Have you ever wondered what animals are thinking?
Show me that love.
I'm David Pogue, and on this episode of Nova Science Now, we're exploring the mysteries of the animal mind. Like, what's really behind your dog's guilty look?
No, bad.
Is it possible that a rat knows right from wrong?
They're not smart enough to share their rats.
They're nice. They share.
People would have probably predicted that this is something that only humans do.
Oh, come on.
What secrets lie in this bird's brain?
Hey, there's a pigeon back here.
How do pigeons find their way home? That is the fundamental mystery.
My hunt for animal intelligence leads in strange directions.
That is a wild slime mole.
There is no way this thing is intelligent.
I think you might be surprised.
Could a hive of bees actually function like the human brain?
Dude, you're sticking your finger in there.
This completely blows away this idea that you have to be really smart to solve problems.
Stay tuned as I'm trapped, kidnapped,
There's no seats in this van.
That's right.
and thrown to the bees.
Where's my bee suit?
All to find out what are animals thinking. Up next on Nova Science Now.
Funding for Nova Science Now is provided by the National Science Foundation, where discoveries begin, and
discovering new knowledge, biomedical research and science education, Howard Hughes Medical Institute, HHMI,
and the Alfred P. Sloan Foundation, supporting original research and public understanding of science, technology, engineering, and mathematics, and the George D. Smith Fund. And by PBS viewers like you. Thank you.
We humans sure love our animals.
She has nail polish on.
And many of us are eager to believe that inside their little heads, they're a lot like us.
Any kind of feelings that I can feel, I believe that BB is able to feel also.
They have a heart, they have a soul, and they definitely could feel what humans do.
And plenty of pet owners are convinced that those feelings include a sense of morality. Do you think she knows right from wrong, then?
I definitely think she knows right from wrong.
I think Parker knows right from wrong. He definitely does.
But I definitely do think they know right from wrong.
Scientists are generally much more skeptical than pet owners. But recently, researchers have started taking this question seriously. And a slew of new studies on different kinds of creatures has been tackling the question, do animals have morals? The results might surprise you. First up, one of the most popular pieces of evidence offered up by pet owners.
I think she can understand right from wrong because if she did something wrong, she has that guilty look on her face.
Ah, yes, the guilty look.
Denver, did you do this? You got into kitty cat's treats?
This video has been seen over 20 million times on YouTube.
Are you sorry about it?
But what is Denver really thinking? Does that pitiful look on her face really mean that she actually feels guilty?
It's really effective. I mean, it's a cute look. It's a definite real look.
Scientists like Alexandra Horowitz, who runs the Dog Cognition Lab at Barnard College, Columbia University, are skeptical. Horowitz wanted to know what the famous guilty look really meant.
The guilty look of dogs mean that they're actually guilty, and it's all about whether dogs have an understanding of right or wrong.
To try to find out, she devised a clever, and I have to say pretty sneaky, experiment.
Right by your toes.
First, she has the dog's owner place a treat on the floor and tell the dog not to eat it.
Stay and leave it.
Then she has the owner leave the room. With the owner safely out of sight, Horowitz has me grab the treat and then lie to the owner. Okay, you can come in. He ate it.
You ate it? I told you not to eat it.
Forget the dog. I feel guilty.
Cody, I told you not to eat it.
Even though Cody has done nothing wrong, there's that look.
Can you look at me? Yeah, you don't want to.
Okay, so you really have to direct her not to eat it.
Yeah.
Horowitz repeated this experiment with other dogs and their owners.
Bad.
And the results were clear.
No.
You know, here's the face I have to give when somebody's yelling at me. And does this indicate that that dog felt that he was guilty?
Finn! No!
No, it doesn't. You know, it indicates that dog knows how to react to that owner.
In other words, these dogs aren't fessing up to anything. They're just reacting to a scolding.
You make it sound like we're sort of being played.
Well, they're learning what works with us.
No. Bad boy.
Does that mean that dogs can't know the difference between right and wrong?
I think it doesn't make any sense to pretend that they understand our moral terms. And I think it's really important to mark a difference between a dog's moral sense and our moral sense and realize they're not working on our terms.
So in this case, even though we might be projecting our values onto our dogs, that doesn't mean that they can't have their own moral sense.
Be a good girl.
In fact, in the last decade, a growing number of new studies are showing us that many animals, not just dogs, do seem to have a capacity for rudimentary moral behavior, to feel empathy and help each other out in ways we used to think were uniquely human. And in the process, they're giving us new insights into the roots of our own morality.
Why are humans moral? What is morality? Where does it come from? Well, we go study animals, and they can tell us a lot about the answer to that question.
Frederica Ranga would agree. She's testing dogs here at the University of Vienna in Austria, and suspects humans aren't the only species with a sense of fairness.
Hi, I'm David.
Frederica, nice to meet you.
Nice to meet you.
This is Guinness.
Ranga is about to teach me how to conduct a simple experiment to test whether dogs have a sense of fairness.
Paw?
At first, I just ask Guinness for her paw
Paw?
and give her nothing in return.
Paw. Paw? Paw?
We do it 30 times without a problem.
Paw? That a girl?
Then Ranga brings in Guinness's pal, Toddy.
Paw?
Now I ask both to give me their paws. But when Toddy does it, I give him a tasty treat.
Dang.
Just as before, Guinness gets nothing.
Paw? Paw? To the good little boy. Paw?
At first, Guinness keeps it up.
Paw?
But after seeing Toddy get rewarded for doing the same thing, she starts to whimper and then goes on strike. Ranga has done the same experiment with dozens of dogs and seen exactly the same result. She believes it's evidence that dogs know when they're being wronged.
If you could write a script for the sorts of things that they're thinking, what would it be?
One possibility is, yes, she says, he's getting food and I don't. Why should I work for free while he's getting rewarded? It's really difficult to avoid the word fairness.
Other experiments with ravens, elephants, chimps, and monkeys are suggesting that we may share moral traits like fairness with other species.
What's really exciting about these studies is this is sort of the first evidence that animals may have a rudimentary, simple form of fairness that then maybe through evolutionary time has then been built upon and has become more complex in our own species.
So it's one thing to know when you're being treated unfairly, but what about apparently selfless acts, like sharing with complete strangers?
Is this Vienna sausage?
Yeah, you can have a piece. Yeah.
People, including myself, would have probably predicted that this is something that only humans do.
That's what Brian Hare, a primatologist at Duke University, used to think. Until one day, when he got a call from his student, Susie Katwenda in the Congo, saying she thought bonobos, a type of great ape, might actually share.
I was like, oh, come on, Susie, there's no way. And she was really insistent, so I said, okay, well, let's do an experiment.
So Hare and Katwenda set up a special situation for two bonobos. One, the stranger, was locked in a room with a key that could be turned only from the other side. The other, in this case Saki, was free to wander around. Then Katwenda places a pile of fruit pieces outside the locked room. Saki has a choice. She can eat all the food herself, or open the door to release the strange bonobo she's never met and possibly give up some of her food.
Think about it. You see somebody at the table next to you with no food. Are you going to go up to the person that you don't know and say, hey, would you like to eat half of the food I just ordered? You know, how many times have any of us done that?
Will Saki open the door for the stranger and share the food?
It's the closest thing that you could think of to doing charity in animals.
So humans might not be the only ones capable of kindness to strangers. But what was Saki thinking? Did she feel sorry for the other bonobo? Was she feeling empathy?
I can't really tell that. All I can tell you is that Saki didn't have to do that. Saki could have just eaten the food. It may be that bonobos just really enjoy eating together. It may not be empathy in this case.
You know what the word
Empathy. It's considered a uniquely human trait, explained here in the classic funny face.
Is it something like sympathy?
Oh, it goes beyond sympathy. Sympathy is to understand what someone feels. Empathy is to project your imagination so that you actually feel what the other person is feeling.
And to demonstrate that uniquely human trait, I've come here to Times Square to test it out for myself on the world's toughest crowd. My kindly producers have shut me into a plexiglass box that can be unlocked only from the outside. I'm totally helpless. Will my fellow human beings sense my distress and help me out? Sure enough, after a few weird looks, my species comes through.
Thank you so much.
Over and over again. Would an animal ever do this? The answer might come from the last creature you'd think to ask. Rats. At the University of Chicago, neuroscientist Peggy Mason is about to show me that empathy might not be just for humans.
Are you going to be empathic today? Yeah.
To test her idea, she's built a special predicament for two rats. One is trapped inside a plexiglass tube with a door that can be opened only from the outside. The other is free to run around, and he's never been taught how to open that door. So you think that Free Rat is literally trying to set free Trapped Rat out of pure human concern?
Or rat concern, as the case may be.
Unbelievable. Look at that! He's trying to figure it out! What the heck? Oh my gosh! And when they see their pal struggling, they certainly seem to work pretty darn hard to get their buddy out.
He is pulling him out.
Come on! He's like,
and
for
now
crying out loud, I got you out, now bust out of here! Mason has run hundreds of rats through these setups, and she's convinced it's the strongest experimental evidence to date of animal empathy.
So it's the first experiment where there's an action that is motivated by empathy. They're using empathic concern to actually help the other rat.
So just how much do these rats really care? Mason wanted to find out. So she did a second experiment to give these rats a moral dilemma.
What we did was we put two restrainers in the arena, and in one restrainer was the cage mate, and in the other restrainer was 5 chocolate chips. And these are rats that were eating, on average, 7 chocolate chips in a sitting. So 5 chocolate chips, no problem.
What will the free rat do? Will he hog all the chocolate to himself? Free the friend? So in theory, we've given free rat a choice.
That's right.
He can either let his pal out of the tube or go get a nice, tasty snack. Checking out his pal. Oh, come on! He let the guy out first. Incredible. And whoever gets there first is gonna gobble it all up.
Will they? Or will they share?
They're not smart enough to share their rats.
They're nice. They share. So on average, the free guy only eats 3.5 chocolates. There's 5 chocolates, so he's leaving 1.5 chocolates.
I might have to think twice the next time I want to call someone a rat.
Our study tells us a lot more about humans than it does about rats.
Come on, you guys, somebody!
What I think it tells us about humans is that we are biologically mandated to be empathically concerned and helping.
The more we're studying animals, what we're seeing is pieces of the moral system that we see in our own species. Now, no species has the whole package, but it basically tells us that our psychology, our brain, it didn't just appear out of thin air. It's actually built on something.
Hello, New Yorkers? What am I, an animal? Yeah, I am. And as long as my species treats me like one, it seems I'll be just fine.
Oh my God, thank you very much. Elvis, ladies and gentlemen.
Help me!
As my mission continues into the minds of animals, I am about to come face to face with one of the biggest mysteries in animal research.
Good.
But first, I have to go through security.
Sent here to take all your electronic devices away from you?
Dude, I am my electronic devices.
For some reason, these guys don't trust me.
That's it. That's all I got, dude.
Oh, well, what's this here?
All right, well, for emergencies.
Uh-huh. All right.
There's no seats in this van, and there's no windows.
That's right.
As I am about to discover, all of this cloak and dagger action is an effort to level the playing field, so I can compete against one of the animal kingdom's most amazing creatures.
Hey! There's a pigeon back here!
My fellow hostage is a Columba leva, more commonly known as a homing pigeon. She may not look extraordinary, but trust me, she is. And she's got a huge secret. If you transport pigeons away from their home lofts and release them, they will immediately fly home. Flying at close to 60 miles an hour, these pigeons consistently complete journeys up to 1,000 miles long. That's farther than the distance from St. Louis to New York. But how do they navigate so efficiently over completely unfamiliar terrain?
Here is a question. How do pigeons find their way home? Been worked on for many, many years, and yet it still is a mystery.
We're here.
Oh my gosh. Where the hell are we?
Dave, it's time to explain the rules.
Yeah, I'd love to know what's going on.
And now I'm getting a real taste of the mystery. Because this guy, pigeon owner Jim Koronek, is releasing the bird and me in a completely unknown location.
So this is Zipline.
Hello, Zipline.
You're going to be racing a homing pigeon.
The race will cover 60 miles. And the finish line is Zipline's home loft in Tempe.
Now, we're going to give you all sorts of help.
Oh, you are?
You get a compass.
Get a compass?
Yes, and then a set of keys to a car. Are you ready, Zipline? Go. If you can get in the car fast enough, you can follow her.
Wait! Oh, I don't even know which way to start. Which road?
Zipline's done this a lot of times. David doesn't have a chance.
Oh no! No, 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 no!
At least I still have my compass. I know that this way is north, this way is south, but wait a second, which way do I go?
I know what to do with this thing!
One would think that a compass might be sufficient. It isn't for a very fundamental reason, which is that the compass tells you where north, south, east, and west is, but it does not tell you where home is.
All I know is that I'm somewhere in a 60-mile radius of Tempe, Arizona. Before I can figure out which direction to drive, I would first need to know where I am in relation to Tempe. Since I've never been here before, even if I could find a road sign or a big landmark, I'd need to locate that on a map and then figure out the direction to Tempe. Scientists know that, just like us, pigeons must navigate using both a compass and a map. Recent studies show that pigeons can sense the Earth's magnetic field and probably use that for their compass.
The thing that we don't understand is what we call the map. How a pigeon taken to some place where it's never been before and released knows where it is with relation to home. That is the fundamental mystery.
The mystery for me is, where in the world am I? Excuse me, do you know how I can get to Tempe, Arizona?
I have no idea how to get to Tempe, Arizona, but I'd love a ride.
All right, hop in. Full disclosure, this hitchhiker is actually a plant. You've met him before. He's Charles Walcott, professor of neurobiology at Cornell and world-renowned pigeon expert.
So I understand you know something about these homing pigeons.
I've worked with them for 30 years.
That probably gives you qualifications to answer this one tiny question that I've got. How do they do it?
We don't know.
Well, but a lot of help you are.
One theory is that the pigeons use odors, smell, to find their way home.
It may sound a bit crazy, but scientists in Italy discovered that if you deprive a pigeon of its sense of smell, it won't make it home.
I think that pigeons use smell to navigate.
Professor Anne Gagliardo believes that from a young age, pigeons get their sense of direction from the odors around their home lofts.
When the pigeons are at their home loft, they learn to associate the odors carried by the winds with the wind direction. And so they build up a sort of map of the environment.
For example, imagine a pigeon knows that in its home loft, the smell of lemon comes from 10 degrees north, and the smell of the sea comes from 100 degrees to the east. When they're taken to a release site, they will search for the smell of lemon and the scent of the sea to get the bearings of both and use these to guide themselves home.
I don't think that's going to help me too much. I'm getting mostly like desert. I still have no clue which way to go home.
The problem with the smell theory is, how can you detect odors over distances of 100 miles? And pigeons routinely home from 500 or 1,000 miles away.
So if Zipline's not smelling her way home, how does she do it? Scientists in New Zealand believe that pigeons use the Earth's magnetic field, not just for their compass, but for their map too.
Well, everything that I've done is pointed to the fact that it is indeed the magnetic field that is the primary candidate for the pigeon's navigational map.
The Earth is completely surrounded by a magnetic field, emanating from the North and South poles. But that field isn't uniform around the globe. Whenever it interacts with magnetic material in the Earth's crust, for example, iron or volcanoes, it bends, creating a magnetic contour map of the world. Todd Dennis and Michael Walker of the University of Auckland have been studying pigeon navigation for years. And they believe that the birds use this magnetic contour map to find their way home. To test their hypothesis, they've been taking pigeons miles from their home lofts, strapping lightweight GPSs onto their backs, and then releasing them from different locations.
Now that we can actually record a track all the way home, we can see this highly detailed responses to the Earth's magnetic field at the release site.
What they discovered is that some pigeons seemed to fly off course for the first part of the journey, and then eventually took a straighter trajectory toward home. It was almost as if they were looking for something. Dennis and Walker believe that what they were looking for was the magnetic contour line that ran through their home loft. Sure enough, when they released pigeons at different locations, each the same distance from home, the pigeons who completed the journey the fastest were the ones who started out closest to the appropriate magnetic line.
I am reasonably confident that, yes, we have cracked this.
Then mystery solved. They detect the Earth's magnetic field.
We don't think so.
The reason he doesn't think that this totally solves the mystery is that he has tested the magnetism theory. Walcott constructed special pigeon helmets designed to disrupt the Earth's magnetic field. Guess what?
Well, they fly straight home. They totally ignore it.
Well, that's two theories shot. So, if it's not magnetism and it's not smell, how do they do it? The answer may lie here, on a hill in upstate New York. It's called Jersey Hill, and it's ground zero in the pigeon mystery. For 20 years, Walcott released hundreds of birds from Jersey Hill, and most of them ended up getting lost.
If we release Cornell homing pigeons at Jersey Hill, only about 10% of them ever come home.
Jersey Hill has no magnetic anomalies, no weird smells, and there's more. Only the birds from the Cornell loft got lost. Birds from nearby lofts had no problem. So if someone could solve the mystery of Jersey Hill, you'd probably finally crack the mystery of the homing pigeon.
It might well be, because something certainly interesting is going on there, and we really don't understand what it is. Here comes somebody.
Excuse me, do you know how to get to Tempe?
No, I'm afraid not. But I can tell you what's going on at Jersey Hill.
What?
Well, in that case, you can get in.
There's something going on here. You're another plant, aren't you?
Yeah, I'm afraid so.
John Hagstrom is a geologist, and he's been studying pigeon navigation for decades.
So let me get this straight. You know about Jersey Hill, these homing pigeons who couldn't find their way back to the Cornell nests?
That's right.
Well, what the heck was going on?
Well, I think the pigeons are using sound to find their home.
Hagstrom got the idea for his theory when he read about an event called the Great Pigeon Race Disaster. In 1997, thousands of pigeons were released in France for a race back to their lofts in England. Almost none of them got home in time.
It turns out that they flew them across the English Channel just as the Concorde, which was leaving Paris, was going supersonic and laying down a boom carpet that these pigeons were caught in.
Hagstrom believes that the sonic boom from the Concorde was so loud that it disrupted the pigeon's navigational system.
So, not smell, not Earth's magnetic field, but sound?
Sound. Infrasound. Low-frequency sound, below our hearing.
So what exactly is infrasound, and why would it be useful to pigeons? Every minute of every day, massive waves in the middle of the ocean are banging into each other with such force that they actually move the Earth's crust 1 or 2 microns. That's a tiny amount, but this movement of the Earth, as small as it is, generates a huge infrasonic noise.
So these birds are somehow navigating by hearing the rumble of the Earth? There's no rumble.
Well, you can't hear it. It's way below your hearing.
Yeah, I'll say.
But birds have very sensitive, low-frequency hearing.
The sound waves from my voice range in frequency from around 100 to several thousand hertz and have a wavelength under a yard long. Infrasonic sound, coming from the Earth's crust, is ultra-low frequency sound, and the wavelengths are over a mile long. These sound waves travel for thousands of miles, and here's the key, every place on Earth has its own infrasonic signature. It would be as if each house on Earth was playing its own radio station. Experiments have shown that pigeons hear infrasound, and Hagstrom believes that the pigeons know exactly what their home loft sounds like infrasonically, and they use that to guide them home. But how does this explain why the Cornell pigeons couldn't find their way home? There was no Concorde jet flying in the neighborhood.
I think Jersey Hill was in a sound shadow relative to the Cornell loft.
Hagstrom studied the atmospheric conditions on the days that the Cornell pigeons got lost. And according to his calculations, the sound from the Cornell loft would have bounced right over Jersey Hill, but not the sound from the other lofts.
So, Charlie, maybe it's not smell and it's not magnetic fields. Maybe it's sound.
Maybe. But again, we need some more experiments to be sure.
So you have some more work to do before you know for sure?
A lot.
All right, so we'll call you back in a week or so?
I'd say in a year or two.
So will it turn out to be sound, or magnetism, or smell?
I think one of the major mistakes that people make is to think that there's one solution to the problem. It's really like the issue of how you find your way home. You use a variety of cues. And I think the same thing is true with pigeons.
All kinds of things happen to pigeons. Dogs, sonic shadows. You just don't know. Stop the clock. I'm here. Where are you? Oh, hello. So you made it back here a couple of minutes before me with your stacked deck and your unfair natural advantage. All right. Well done this time, buddy. Let's see you host a TV show.
What is intelligence, anyway? Forget about humans. Forget about anything with a big brain. Scientists are discovering a group of creatures that's forcing us to reconsider what it means to be intelligent, even what it means to think. So who are these fine specimens?
This? Are you kidding me? You dragged me out here to look at this?
That is a wild slime mold.
A wild slime mold?
That's right, slime mold. If looks can be deceiving, then slime mold is the master of deception. It's no ordinary single-celled creature. It's a collective of cell parts working together as one to do extraordinary things.
There is no way this thing is intelligent.
But it is. I think you might be surprised. It is smart.
Anne Pringle is an expert in fungi and slime mold at Harvard University. And she's about to show me just how smart these guys can be.
All right, let's give it a go. Ready? There's your pen.
What is this?
You're gonna erase the maze, and the slime mold is too, and we're gonna see who does a better job. 3, 2, 1, go.
All right.
Having trouble?
Quiet.
It's not that hard, but I had to double back a couple of times.
Done! In the time it took me to solve this puzzle, your slime has done nothing!
Sometimes it's not about how quickly you do things, it's about how well you do them.
It may take this goop over a day, but it finds the shortest path through the maze more efficiently than I did, without any mistakes or going back. All without any brain or nerves whatsoever. The slime does it by communicating across its body of thousands of cell nuclei. By working together, the collective of dumb parts can do pretty smart things.
This completely blows away this idea that you have to be really smart to solve problems. The intelligence emerges from the interactions among much simpler components.
And that's just it. Slime mold, as it turns out, is just one of a growing number of creatures that scientists say possess swarm intelligence, a kind of intelligence where many individuals work together as one to do amazing things. Understanding how these organisms do it could fundamentally change the way we think about the evolution of intelligence.
We used to think intelligence was really associated with having one large brain, whereas now when we look at swarming ants or bees or schooling fish, we realize you can build intelligence in other ways.
A single fish isn't too bright, but by abiding by simple rules, like swim close but not too close, stay lined up, and avoid things you don't like, the school can outsmart even the most cunning predators. And some scientists now think our brains might actually work the same way.
Each neuron in your brain isn't smart, yet collectively, you're very intelligent. How is that possible? Are there parallels between these systems and how the brain operates?
Now, one scientist thinks there are, and he has evidence to prove it.
Land ho!
Cornell biologist Tom Seeley is taking me to the secluded Appledore Island off the coast of Maine.
This is Appledore Island. Without this island, we couldn't have done this analysis.
Wow. Where he thinks he's discovered an alien brain to rival our own. No, it's not from another planet. It's bees.
Tom, where's my bee suit?
Well, you won't need a bee suit here, David.
What are you doing? Dude, you're sticking your finger in there.
Right. You, too, can also put your finger in there and can
No,
feel...
I can't.
There you go.
Oh, my. Oh, my
Yep. There you go.
Sorry.
Apparently, these bees aren't stinging me because they're focused on finding a new place to live. House hunting bees are Seeley's specialty. And after 37 years of study, he's convinced that swarms like this not only make smart decisions about where to live, the way they make those decisions bears uncanny resemblance to the way decisions get made in our own brains.
Tom Seeley is finding that there are deep parallels with how the brain makes a decision with how the bee colony itself can make decisions. This is extremely important because it's telling us something fundamental about how you can build intelligence.
So let me get this straight. You're saying that these bees make a decision. Dude, they're bugs.
That's right, that's right. Collectively, they can achieve high intelligence. It's a lot like how your brain works.
My brain? How could that be? To understand Seeley's far-out claim, we have to look at swarming bees like this. These 12,000 bees have outgrown their old home and need to find a new one to build their hive and raise their young. Normally, a swarm like this would pick a roomy tree hole, but here on Appledore Island, there aren't any trees, so Seeley can do controlled experiments with wooden nest boxes to figure out exactly how the swarms make this decision. To start, Seeley places 2 boxes out on the island, about 1/4 mile away from the swarm in different directions. The first, labeled yellow, is a dream home for the bees, roomy with a small entrance to prevent predators from getting in.
There we go.
The second, blue, is a fixer-upper. It has less space inside and a big entrance.
Take out this little entrance, put in a big entrance. Okay, all set. A so-so home site.
Back at the swarm, a few scout bees take off in search of a new home. As soon as one discovers the yellow box, Seeley's team nabs it and gently dots it with the corresponding paint color. Same goes for blue. What happens next, I have to say, is pretty crazy.
Each bee that finds something comes back and announces her discovery by performing these waggle dances.
Wait, waggle dances?
Yes.
As it turns out, the waggle dance is the way bees communicate with each other, and its discovery back in 1946 was so astonishing that it won a Nobel Prize. See our yellow painted bee here? See how every time she wiggles, her head is facing the same direction? She's actually pointing her hive mates in the direction to fly to find the yellow box. Similarly, our blue bee is doing the same thing, but in the opposite direction, pointing the way to find the blue box. Those bees tagging behind her watch carefully so they can follow directions. They take off, check out the real estate for themselves, get marked, and when they return, more dances, more recruits. But the blue bees are at it too. Now we're getting more and more painted bees back at the swarm. But that's not all. Notice how our yellow bee is doing the dance 3 times, while our blue bee is doing it only twice. Again, that's 3 times for yellow, but only twice for blue. This last piece of waggle speak tells us how enthusiastic they are about their sights. Looks like yellow is picking up more recruits. And the yellow box is the better home. Will yellow win?
Wow. So how is the decision made then?
It's a lot like an election. The bees try to recruit additional supporters to be affiliated with their site.
And scientists thought that when enough bees waggled for a particular site, that's how the swarm would decide where to move. But then Seeley uncovered a new part of the process. See this yellow bee here? She keeps ramming the blue bee and making that weird beep sound. It's a signal that means stop dancing. And if she keeps it up, the blue bee will eventually stop dancing for the blue site.
The bee version of mudslinging, negative campaigning.
What Seeley discovered is that bees like this will go around using this stop signal in addition to waggle dancing, thereby campaigning for their own site and curbing the competition. Amazingly, this process is what neuroscientists believe mirrors how decisions get made in our own brains.
We think there is very clear evidence for the human brain that individual neurons firing in one group at the same time prevent firing in the other group.
Here's how it works. Let's say I'm trying to decide whether to eat cake or broccoli. Even though I am not conscious of it, there are a bunch of neurons in my brain that are firing in favor of cake and another set firing for broccoli. But that's not the only signal they're sending. The pro-cake neurons are also sending chemical signals to inhibit the broccoli neurons to stop them from firing. And vice versa. This combination of positive and negative signaling is what neuroscientists call cross-inhibition, and they think it's critical to the decision-making process.
We don't have all day. We have to decide. We have to move on. Cross-inhibition is critical to the process of making effective, rapid choices.
So both bees and brain cells seem to use the same strategy of positive and negative signaling to reach a decision.
Tom Seeley's studies of bees suggests evolution is finding the same solution to problem. I find that mind-blowing.
Once the decision is made, all the bees will go to one new home. The trigger is the number of bees visiting a candidate site. As soon as it hits around 100, those bees report back to the swarm, and it's go time.
So something is happening. They're getting really agitated.
Yes, they're about to
Oh my
launch
gosh, are you seeing them peel off like that?
Yeah, this whole swarm cluster is going to dissolve. These bees have finished making their decision. They finished making their preparations to fly to the new home, and now they're starting
I'm sorry,
to
I can't hear you. These guys are getting so loud.
So who is the winner? Did the bees pick the best new home?
It's getting deafening. There's 12,000 bees. Look, they're all evaporating. Look at this. All at once. This is unreal. This is unreal.
This is real. You know, it's like discovering a manuscript by Mozart, something like that. Even though the decision-making in a swarm of bees has evolved completely independently from the human brain, they've converged on the same basic design, which tells us that this is probably because this is the optimal way to do it.
Off the coast of Puerto Rico, there's an isolated island kingdom ruled by our distant relatives. Very distant. On Cayo Santiago, rhesus monkeys reign. But today, they're getting some visitors. Lori Santos and her team of researchers. The Yale cognitive psychologist has made a career out of studying monkeys. And while she spends most of her time on campus and in the classroom, where she recently won a top teaching award, her favorite place is Cayo.
For me, I have this moment of just feeling completely at home. It's like, my monkeys. That guy's checking me out.
Lori wants to know what monkeys are thinking, and monkeys on Cayo Santiago are the perfect subjects. They were brought from Asia in the 1930s to populate the island for behavioral research. Originally, there were only 400. Today, more than 1,000 live here.
This is a fabulous site for research. We know who's related to who, we know all the information about where males were born. We can get these big populations and really see variation in how the individuals interact and what they know about the world.
Before Lori could understand their thoughts, she had to understand how things work on the island.
Here's Josh, my buddy. Go get some food, bud. It's just like seeing old friends. Oh, look at you, you grew up so well. Oh, you have a kid now, it's great,
She has come to understand their monkey society, complete with insiders, outsiders, queen bees, and wannabes.
There's 6 different social groups on the island. The groups can sometimes have tensions.
The alpha group rules the island, and its members get first dibs at whatever they want, including the monkey chow humans feed them. They show their status at the feeding troughs. Beta groups hang back until the alpha group has had its fill.
You see just a ton of monkeys who are just kind of waiting in the wings to get some and kind of scared. It's really like human nation states where access to resources is controlled by who you happen to be and what group you happen to be in.
Lori's groundbreaking work on monkey behavior has gotten a lot of attention. But why spend all this time unraveling the monkey mind?
I want to start my talk today with 2 observations about the human species. They give us a much broader window into the evolutionary history of humans. By studying monkeys, we can go back 30, 40 million years. You can really get at what they know about in the world in this way that's sometimes really pure.
And while the human brain is larger, the monkey brain shares much of the same circuitry and features as ours. So they're related to us, but they aren't weighed down by our cultural baggage.
These experiments can tell us about our shared history with not only monkeys and apes, but with other animals.
But last time I checked, monkeys can't talk. So how does she ask them questions about what they know? She gives them tests. Some involve lemons, others grapes. Anything to catch their attention. As a child growing up in New Bedford, Massachusetts, Lori's attention was captivated by animals and people.
I guess as a child, I was sort of a budding anthropologist. I was always kind of messing with human behavior and animal behavior to see how it worked.
But she didn't only mess with animals.
I think my brother felt like, he was my experimental subject. So it was easy to kind of dress him up and make him do stuff on the video camera.
All in the name of science.
The biggest thing from my childhood that translates into what I do now is just a rich curiosity for people and how they work. It was both a curiosity and this urge to figure out ways to test it.
Lori's curiosity paid off. The valedictorian got a scholarship to Harvard, where she quickly found her niche when a professor showed her pictures of his research site, Cayo Santiago.
And I was like, I'm going there. I've been going there ever since.
Lori's been traveling there for nearly 2 decades. But one thing she noticed right away: monkeys are thieves. The lemons she used in some of her experiments kept disappearing whenever she looked away.
And then you realize there's some monkey running up the hill with the fruit.
Humans know that stealing works only when no one sees you do it. Lori wondered if monkeys understood that too. For decades, the scientific community has debated if animals can understand what goes on in another's head. Like, does your dog know what you're thinking? Monkeys knowing to steal from you when you're not looking suggests that they do. But how could Lori prove it? She decided to find a monkey alone and bait him.
There were 2 human experimenters. Each of them had a grape, which monkeys think is absolutely delicious.
Take, kebab, step,
They then put the platform with the grape on the ground in front of them.
Down, up, turn.
The experimenters dressed and behaved identically, except one turned away and one faced the monkey. Lori knew that if the monkeys stole from the person turned away, it meant that they understood who couldn't see them. She tested over 100 monkeys and took data with her camcorder. And whom did they steal from? The person who's not looking. In fact, 90% of the time, they stole from the person who couldn't see them.
So what this study tells us is that the monkeys are actually taking into account where a person's looking and using that to figure out what that person knows and what he doesn't know.
It's a concept called theory of mind, and Lori's stealing study made headlines, proving that monkeys share at least one important aspect of it with us.
And that's a really powerful mechanism. It allows them to deceive others, to be tricksters and cheat. And they only do certain kinds of activities, specifically the kinds of things they're not supposed to be doing when others can't see them.
Like stealing food from each other, or mating with off-limits females in spots where high-ranking monkeys can't see them. Monkeys having the capacity to understand what others can see and know is an ability that humans use often, especially Lori, who's fond of observing her own species.
I think one of the coolest capacities we have is to really take on what it means to be somebody else, how they think, how they make sense of the world, what they know.
But how will understanding why monkeys behave the way they do affect us?
We know lots about how our psychological mechanisms lead us astray. We know really little about where those mechanisms come from. Maybe some of the strategies we're using are evolutionarily old.
Which means some of our behavior is ingrained in us and more difficult to change. But Lori thinks not impossible. And she's leading the charge to find out if we can change our own behavior in the future.
If you think about how much we've learned in science about the tiniest particles out there or the biggest galaxies out there, right? We know how those things work. We still can't predict behavior. We are just terrible at understanding ourselves. If we really want to understand humans and we really want to change our behavior, we have to understand how we work.
And now, we'd like to hear from you. Follow us on Facebook or Twitter, or join us at pbs.org/Nova Science Now.
You can see any of these stories again, watch exclusive short videos, hear from experts, and check out our web-only series, The Secret Life of Scientists and Engineers.
Well, that's our show. Hope you've enjoyed this episode. We'll see you next time on Nova Science Now. Okay, dude, I need the bee suit.